So continuity is talking about whether there's any breaks in a function at given values of x. And to satisfy continuity, the function has to exist, the limit has to exist, and the limit has to equal the value of the function. Before I forget, Christian, that jump drive I gave you, we put that stuff on the other day, was actually not your jump drive. Do you have it today with you? It's your house, yeah. Can you bring it in Thursday? I'll let you use his jump drive. It's actually Patrick's because I found one in my bag, and I was like, whose jump drive is this? And I looked at there was some paper on there, and your name was on it. So I think we got them confused. I got them confused. So anyway, um, so what I'll do is I'll let Patrick use this until Thursday. It has the calculus stuff on there. Okay, so there are certain properties of continuity. If you have two functions, f of x and g of x, and if they are continuous at some value of x equals c, then if you do these things to the functions, they remain continuous. So you can't destroy continuity by just multiplying by a constant. That makes sense because if you have a value of the function and you increase it by twice as much, that's all it does. It doesn't change whether there's a break or not. And the same with if you have two continuous functions and you add them or subtract them from each other, that also stays continuous. If you have two continuous functions which you multiply together, or continuous at x equals c, it doesn't have to be continuous everywhere, but if they're continuous at some value of x, then the product of those two functions remains continuous, and the quotient remains continuous as long as the value of the function does not go to zero. The value of the function in the denominator doesn't go to zero at x equals c. So that would cause a discontinuity, but otherwise all these other arrangements remain continuous. I have this is my stuff I made up, the Nicholson properties of discontinuity. This is if you have one function that's continuous and another one that's discontinuous. So if you multiply a discontinuous function by a constant, it's still discontinuous. So it just makes it discontinuous, just lists everything up just like before. If you have a discontinuous function and a continuous function, by adding two functions together, it doesn't remove the discontinuity. If you multiply a continuous function by a discontinuous function, the product is still going to be discontinuous at the same point that it was discontinuous when it was just one function by itself. And the same with the quotient. So I just made that up just because I thought it was interesting. Okay. And the continuity of a continuous function, this is theorem 1.12. It says if g of x is continuous at c and f of x is continuous at c, then the composite function given by f of g of x, or f of g of x, is continuous at c. So what does that mean? Let me just give you an example. Let's say f of x equals x squared, which is continuous because it's a polynomial. And let's say g of x equals the sine of x. So if you do f of g of x, that would be the sine of x. So what you do is you substitute for x, you put in g of x into the function f of x, so it becomes sine of x squared. So what it's saying is that if this is continuous, which it is, and if this is continuous, which it is, then the composite function sine of x quantity squared is also continuous. Now, you learned a little bit about these composite functions in pre-calculus, and mostly what you learned about, I think, was domain and a range, how the domain of one influences, say, the domain of g of x influences the composite function f of x, f of g of x. That was about it. It turns out in calculus that composite functions are much more prevalent in understanding calculus. That's all you need to know right now. So you'll see composite functions a lot in calculus, like this. This is a composite function. Okay, so all these theorems are interesting. You'll learn to use them where they're appropriate. You won't have to memorize them. You can just look in your book and get that information. So the first part of this section was about continuity. Okay, yeah. We also talked about removing discontinuities by defining the function at the discontinuity, and that only applied for cases where you had indeterminate results. One thing you also need to know how to do is determine where certain functions are discontinuous. So these are the places that you would check. So if you had a function where a value of x makes the function indeterminate, where you get 0 over 0 or infinity divided by infinity, the function is not defined at those points, and because it's not defined, there's a discontinuity at that point. Those are ones that are most likely to be able to have the discontinuity removed, like we did last time. The second place that you see discontinuities is where the function goes to infinity or negative infinity, and that occurs when you divide a non-zero numerator by 0. So these are things like rational functions. Also, the 4 other trig functions. Because if you think about, you might say, well, yeah, I understand the thing about discontinuity. I mean, about rational functions, but I'm not sure about trig functions. What's happening is my headphones are ringing, which means they're about to die, and I forgot to bring my cable. So let me I've got to run. Okay. So if you think about something like the tangent of x, in terms of the other trig functions, the sine of x or the cosine of x. So in that case, the cosine of x goes to 0 at some point where the sine doesn't go to 0. So you are dividing by 0. If you have the cosecant of x, which is 1 over the sine of x, that goes to 0 as well. So these are all rational functions involving trig functions instead of involving polynomials. So if I wanted to find the values of x where the tangent goes to 0, all I have to do is figure out the values of x where the cosine is 0. Is discontinuous. I don't know what I said there. If I want to find the place where tangent x is discontinuous, I find the values of x where the cosine goes to 0. If I want to know when the cosecant is undefined or discontinuous, it would be where the sine of x equals 0. So that's, and then finally, if they're a stepwise function like a absolute value type problem that we've talked about. So these are where, usually what I do to test you on this is I give you a rational function and you have to just factor the denominator and find out the values of x where it goes to 0 and say there's a discontinuity there. So that's pretty much what's involved in doing that. So here's a couple of examples. Here's a rational function. And, initially, this one may look like, I just have to say x is equal to 5, but you can't do that. You have to factor it, see whether it's undefined or whether it's indeterminate or neither one. So if I factor the numerator, I'll have x minus 5 times x minus 1 divided by x minus 5. So this is determinant at x equals 5, so it's discontinuous, at x equals 5, but it is a removable discontinuity. So I could remove the discontinuity if I wanted to. Okay. Now here, the second case, again, we have to factor it to see which. Don't always assume that this is the answer. You always have to factor it. The numerator is the same, so it's not too hard to factor. In that case, there is no indeterminacy. So in this case, for the second one, you'd say it's undefined at x equals -2. And it's also discontinuous at x equals -2, but it's a non-removable discontinuity because it's a vertical asymptote. Okay. I'm going to make one up here. If I did f of x equals the secant of x, in that case, I would rewrite it as 1 over the cosine. So it's undefined at x equals pi over 2, 3 pi over 2, and you could say it's equal to pi over 2 plus n pi. So that gives you, and I guess you'd have to define n. So n, actually, I'm going to say n is the set of all points where you go from -infinity and something like that. So you can have n be a negative number or a positive number, so that gives you an infinite number of discontinuities. So it's undefined. I mean, it's undefined and it's also discontinuous at these values of x, and it's also a non-removable discontinuity. Yeah, that's all right. Sounds reasonable. Okay, and the last thing we're going to do in this section is this intermediate value theorem. So I'm going to read the definition for the theorem. It's on page 77 in your book, and then I'll explain what the significance of it is. If f is continuous, which is a function, f of x is continuous on a closed interval, which means that it includes a and b and everything in between a and b, and k is any number between f of a and f of b, so that's a y value that's between the value of the function at the beginning of the interval and the value of the function at the end of the interval, then there's at least one number c, and this is the x value in the closed interval a to b such that f of c equals k. Okay, so what does that all mean? So let's just draw a picture. Picture's worth 1,000 words here, or at least how many words? 20-some words. So you have a function, which we'll assume is continuous, so there's no breaks in it, no vertical asymptotes, no holes, and there's some x value equal to a, which defines the beginning of the interval. There's some x value b that defines the end of the interval. The y value at x is you just go up to the curve, and so this horizontal line from where this vertical line intersects the curve is f of a, And if I go over here, that's f of b. It says k is any number between these two. So here's k. It's any number between here and here. It says then there is at least one number c. So if I draw horizontally over here, then there's, if you go the other direction, so you define y, go over to the curve, figure out what the x value is. This is x equals c. It says there's at least one number c in the interval a to b, such that f of c, so here's, if I go the other direction, here's x equals c, it turns out that f of c equals k. So here's my explanation of the intermediate value theorem. No, can't move because I'm connected. Well, let me grab my glass case. So here you have a skydiver. He jumps out of a plane, 2,000 feet. And let's say 20 seconds later, he's at 1,000 feet. What the intermediate value theorem basically says is that if he starts at 2,000 and he ends at 1,000, that he's got to go through every elevation in between. He doesn't transport. It's not like Star Trek and they puts him in a transporter and he goes here and suddenly appears there. He's going to go, if he's a human being in the real world, he goes through we know that he passes through every elevation from 2,000 to 1,000. That's pretty much it. Okay. In this case, the x value is the time. Time is continuous, and he's going to pass through everything. So that's all it is. Where is this useful? We'll find out later. Okay. So it's just you have to introduce these things in math so that when you get later on, you have the background to do it. But that's basically the intermediate value theorem. And that's my little demonstration. Skydiving example. There's your homework. So there's not a whole lot. I think most of it's just, these are probably finding removal of discontinuities. These are probably identifying where there are discontinuities. I don't remember exactly what they are. It's been a while. Now, 79 and 81, only using a graphing utility to zoom in. So you can use the graphing utility. Well, you can't yet because you're not in Blackboard. But you can use your graphing calculator just to graph the function and then just use that to answer the question. You don't have to answer the rest of the question. Just zoom in using your graphing utility. So write that down, and when you get to the problem, it'll make sense why I say that. It just makes the problem easier. So these will be due next, what is today? Tuesday, next Tuesday. We're almost at a point I can start thinking about when our first test is going to be. So we're going to be finished with Chapter 1 this week. So I'm going to tentatively say that next Thursday will be the first test. It'll be on Chapter 1. I don't see any reason why I'll change it, but I'm not guaranteeing 100% chance. But we don't have class Monday, that's true. But it won't be any earlier than next Thursday. How about that? If it isn't Thursday, it'll be the following Tuesday. It's always either on Tuesdays or Thursdays. Okay. We alluded to this last time about one-sided limits and rational functions. So that's basically what the next section is about. And then we're ready to, once we learn about limits, then we can, yeah, it's section 5. So we can then move on to derivatives. actually some real calculus. So we're going to talk about infinite limits. They're basically the limits when you have add a vertical asymptote. So you have infinite limits when you have a vertical asymptote. And you have vertical asymptote when you have a rational expression where the denominator is 0 for a given value of x, but the numerator is non-zero. And basically all we're doing in this case is we want to figure out whether the function is going to positive infinity or negative infinity. That's the whole concept here. We don't care how fast it goes to positive infinity. We just want to know whether it's going to positive or negative infinity. So it's really just a matter of looking at signs of various parts of rational functions. And so here's a picture. So this is 1 over x squared. And if I plot it, it's obvious. They're going to which positive infinity or negative infinity? Positive infinity. Okay, everybody knows which positive is, hopefully, on the graph. Now, if we actually just ask the question, what is the limit of this function, 1 over x squared, as x approaches, in this case, 0, we would say the limit does not exist. And that's because if we come from the left-hand side, we are approaching infinity, but we say it does not exist because infinity does not exist. But if we wanted to look at the one-sided limits, if we said what is the limit as x approaches 0 from the negative side of 1 over x squared, or we wanted to know what the limit as x approaches 0 from the positive side of 1 over x squared. This is what I said the other day. We make an exception. So on one-sided limits at vertical asymptotes, we either say it's positive infinity or negative infinity. We don't say it doesn't exist. If we're talking about the limit itself from both sides, we say it does not exist. Because in this case, yeah, they do both go to the same, they both go to positive infinity, but if the asymptotes go the opposite directions, then they don't go to the same thing. And so we just say it doesn't exist. But for one-sided limits, we say it's true. It is okay. And so the answer is positive infinity. I'm going to pop positive infinity just because the other option is negative infinity. So it's just emphasizing that it's going up, even though you don't really need that officially. So that's how you would do it graphically. How would you answer that question numerically and I guess really just numerically? Well, one way you could do it is you could make up a table and you could pick values of x that get closer and closer to, and I'm not sure why I needed 3 columns, but let's redo that. I think I just need 2 columns. So what you would do is you just make up a table, and this would be x, and this would be f of x. And so you would pick values, say that you wanted to know what the limit as x approaches 0 from the negative side of 1 over x squared. You would pick, negative 0.1, negative 0.01, negative 0.001, and so here you would get 100, and here you would get 10,000, and here you would get 1,000,000. I'm pretty sure that's the way it works. Is that, I got one more 0. Because I'm squaring it. So I'm taking 1 over a tenth. Well, 1 over a tenth is 10. 10 squared is 100. But because I'm squaring it, the negatives become positives. And so, obviously, as x gets closer and closer to 0 from the negative side, you're going to approach positive infinity, which we saw over here graphically. The reality is, though, that I don't really need to go into this much detail. I could just say, let me just pick some point close to 0 and just check one point. And if that one point is positive or negative, then that's going to answer the question. So I wouldn't go to all this trouble. What I would do is I would say, what is f of negative 0.1? And that would be 1 over negative 0.1 squared. And I really don't care ultimately what this value is at negative 0.1. All I care about is it positive or negative? So I look at this and I say, well, I've got negative 0.1, so it's negative. That's the important thing. So I really can say this is negative. I'm just going to put a sign here and I'm going to square it. So instead of putting the number in there, I'm going to just put a negative sign. And because if you have an even exponent with negatives, you get a positive, and if you have an odd exponent with negatives, you get a negative. So because this is even, I know the final answer is positive. And so I can say, therefore, just by looking at the signs, that the limit as x approaches 0 from the negative side of 1 over x squared is equal to a positive infinity. So I use this information to then define whether it's positive or negative infinity. And that's all I'm really trying to do. So instead of making up this little table, I could say, well, if I want to know what the limit is as x approaches 0 from the positive side of 1 over x squared, what I would do is I would say, okay, I have 1 over positive 0.1 squared, and that's 1 over a positive number squared, which is a positive number, and therefore, to answer the question, the limit as x approaches 0 from the positive side of 1 over x squared equals positive infinity. So I use this to then define that. So anytime you have a vertical asymptote, all you have to do is just go a little bit to one side, either to the left-hand side or the right-hand side, depending upon which limit they're asking you for, and then just look at the signs of the different parts of the rational function to figure out whether the total product of pluses and minuses is a plus or a minus. So once you get that answer, then you can answer the question about the limit. That's the basic concept here. So let's, okay. So we'll do another example, but and don't write this down, just pay attention to this. So be sure you understand that the equal sign in the statement that the limit of f of x equals infinity does not mean that the limit exists. On the contrary, it tells you how the limit fails to exist by denoting the unbounded behavior of f of x as x approaches c. Okay, so when I say the limit as x approaches 0 of 1 over x squared equals, from the positive direction, is equal to plus infinity, that doesn't mean the limit exists. So the equality doesn't mean the limit exists. The fact that the equality is infinity denotes that the limit doesn't exist. Okay, so it's a fine point, but you might say, well, you equal something, so it must exist. But the equality doesn't mean the fact it equals an unbounded quantity means that it does not exist. But it allows us to tell us whether the asymptote is going up or going down. It's just a convenient. And you also have to be careful, as we said, if both the numerator and the denominator are 0 at this value, you're not, you don't have unbounded behavior. You have an indeterminate result, and therefore you have to use the techniques from section 3 to determine what the limit is. So always check to see whether a rational function has the same factor in the numerator and the denominator, or just plug the number in and see whether you get an indeterminate result. If it is indeterminate, just because the denominator is 0 doesn't mean that it's unbounded. It just, in pre-calculus, we never really looked at this, but in calculus, you have to be really careful about not jumping to conclusions too quickly about the limit. Okay. So let's just do a more complicated rational function, and then I've got a handout. We'll practice some stuff here. So let's say, what is the limit as x approaches 3 from the negative side of this function? So we're going to have x plus 7 times x minus 2 divided by x minus 3 and x minus 5. Okay, so it's a rational function because the factors in the denominator do not exist in the numerator. We know that we don't have any cases of this indeterminate behavior. So we know now by comparing these factors this direction, we know that these two factors are going to result in vertical asymptotes. One of them is going to be at x equals 3. So I know if I plug 3 into here, I would end up with some number divided by 0, which means that it does not exist, but it could not exist in one direction or the other. So the way you answer this question is, the question is it equal to positive infinity or negative infinity? Question mark. The easiest way, of course, would just be to plug this in a graphing program. But what we could do, we could choose to evaluate f of x at x equals 2.9. Why did I choose 2.9? I heard somebody. Yes. Yeah, it's close to 3, but it's less than 3. Okay. If I was taking the limit from the positive side, then I'd choose something like 3.1. So let's do it the long way. So then what you would do is you just evaluate the function at 2.9. But we really don't care about whether it's what the value is. All we care about is taking this information and determining what the sign of each of the 4 factors are. So what is the sign of this? That's always the easy one, right? A positive number plus a positive number is a positive number. So I just put a positive sign inside parentheses to represent the sign of this term. Okay, is this a positive or negative number? It's positive because 2.9 is greater than 2, so that's positive. Is 2.9 minus 3 positive or negative? Well, that's negative because this number is less than that number, so that's negative. And 2.9 minus 5 is going to be negative. So if I look at just the signs, I've got 2 positives and 2 negatives. Well, positive times positive is always a positive. All you really have to do is count the number of negatives that you have, whether it's in the numerator or the denominator. So I've got 2 in my total equation, therefore that's an even number, and therefore the final answer is positive. So what we can do, we can say therefore the limit as x approaches 3 from the negative side of my function here is equal to positive infinity, and that's your answer. So that's basically the procedure. Now, there's actually, you can do it slightly easier or slightly easier, okay? What if I looked at the signs instead of, in all the cases that are not the factor that goes to 0, which is this one, okay, if I just plugged in 3 instead of 2.9. So if I did 3 plus 7 and 3 minus 2, and then I do, for this one, I do 2.9 minus 3 and 3 minus 5. I'm going to get the same answer. 3 plus 7 is positive 10. 3 minus 2 is positive 1. This one is still negative. That's one I have to think about a little bit. Not negative 1, but negative. And this is 3 minus 5 is negative. So I still get the same result. It's just I don't have to worry about 2.9 plus 7. It's easier just to, if I'm trying to conclude whether this term is positive or negative, if you use a whole number, it's going to be a lot easier than if you use a decimal. So you still get positive, and therefore you make the same conclusion. So either way is fine, depending upon how you feel about the whole thing. But I want, when I give you a test question like this, I want you to show me the signs of each part of the rational function like this, however you determine it. And so you come up with the result, and then you use that result to answer the question. Okay, so that's the basic concept here. So let me hand this thing out. There's the first problem. So all you have to do is look at the limit, the number you're taking the limit towards, and the positive side. So what you want to do is you just want to, I'm going to plug in -2 into the rational expression. And then I'm going to ask you questions about whether it's positive or negative. Just go around the room, starting somewhere. So for this factor, you have to use something other than -2 because it'll go to 0. So it's -2 from the positive side. So that is -1.9. So from a number line perspective, this is -2. This is positive. This is the negative direction. Therefore, the positive side of -2 is here, which is -1.9. Okay. So, Jacob, what's the sign of this term right here? Negative. Okay, so let's write the signs down here. Negative. Okay. Who's next? Kelly, what's the sign of this one?
Positive.
Yep. Positive. And Great. Negative, yeah, that was the easy one, 'cause this is no. Okay, Maya? Oh, sorry, yeah, this next one, that's negative. And then we divide by, okay, Michaela, so this one is positive. And Margaret? Positive, right. So the question is the answer positive or negative? So, negative because?
There's an odd number of negatives.
Right. And it doesn't matter whether the negatives are on the top or the bottom, you just count them wherever they are. And that's because, anytime you multiply a negative times a negative, you get positive. So with an odd number of negatives, is always your leftover negative, which makes the whole thing negative. So from that, you come up with the negative, and therefore you can say the limit, in this case, the limit of, I'm not going to write it out, the limit of f of x as x approaches negative 2 from the positive side is equal to negative infinity. Okay, so that's pretty much it. So before I let you go ahead and do it, let's just look at the what this function looks like. I mean, it's kind of a complicated looking rational function, but it's not crazy, super crazy. Okay, so what is it? Wish I had my paper so I could. X plus 1, x plus 7. Okay. So you have x plus 1 times x plus 7. That's not right. X plus 7. And the next one is x times x times x minus 5 divided by x plus 5 divided by x plus 2. So graph this rational function. Well, I divided twice, so I could have done this, or you can divide by. So that's what you were thinking of. You got to make sure you. But if you divide it each time, you get the same answer. So you see, you get the same answer. Okay, so this is what it looks like. Let's zoom out a little bit. So there is. Yeah, I tricked myself. No, I didn't. There should be a vertical asymptote at -2 and -5. So unless I made a mistake, it's just we got to zoom out further in the x direction. There we go. So there are actually two vertical asymptotes. You don't, unless you zoom out, you kind of get confused. So there's a vertical asymptote here at x equals -2, and there's a vertical asymptote at x equals -5. So what we were looking at is what is the limit as x approaches -2 from the positive side, which is, this is -2 from the positive side, and you can see that the function approaches negative infinity. So that's what we're looking at. We're looking at the behavior of the graph as x approaches 2 from the right-hand side, and that does agree with what we came up with. Okay. But yeah, when I first looked at that, I thought, did I put something in there wrong? Because you just don't see the vertical asymptote initially until you really zoom out. Okay, so go on to the next one and try the same arrangement. I'll copy it, and I'll give you a few minutes head start, and then I'll so what you're going to do is you're going to plug x equals 3 in everywhere except right here, and you're going to pick a number that's on the left-hand side of 3, which would be, what number are you going to pick for this one? 2.9, yeah. So while you're working on that, I'm going to copy these to my okay, disconnect me. I think I can walk around now. Do you understand what's going on? Good? Everybody okay? Oh, you're already done. Wow.
Are they all right?
I don't know. I have to work through them and see what the answer is. Did I got that one right? So the second one I got positive infinity. So these are I plugged in x equals 3 into those. And, once you've done them a few times, you can almost just look at it without even writing these things down. You can just write the pluses and minuses. I can go up here and say positive, positive, negative, positive, negative, positive, negative, and then I have to think a little bit harder about this one because that's the one where I have to put in a number slightly less than 3. So that's negative. So I ended up with 4 negatives. So that was an even number. So that gave me a positive result. Everybody agree with my third one? Just got to be careful here. You've got negative times a negative. So that's positive. So you get 4 plus 3. So that's positive. Negative 3 plus 2 is negative 1. So that's negative. This is positive. 5 minus 3 is positive. Negative 3.1. So it's negative 3 on the negative side. So it's more negative. So you get a negative, this negative number is greater than that positive number, so it's a negative, and then two negatives give me a negative. I've got odd number of negatives. And then the final one here, so you got 7 plus 8, 7 minus 3, 7 plus 2, 4 minus 7, 7 plus 1. So it's 7 greater than 7, so 7.1 minus 7. 7 minus 10. So that's positive. This one's positive. That one's positive. That one's positive. That one's negative. That one's positive. That one's positive. That one's negative. So I've got an even number of negatives. So it's positive. And therefore the limit as x approaches 7 from the positive side of this function is positive infinity. Okay, so you guys can hand that in, not now, but when you leave. So let's see if I've got any homework for you for this section. I'm going to go ahead and assign the homework, even those, yeah, there you go. So you have something to work on in your study session. So this will be due next Tuesday as well. We'll come back and review it a little bit tomorrow, and then we'll move on to chapter 2. So I think we're done for today. So I'm going to write that down, my book. So let's see what's due coming up here. So 1.2 is due Thursday. 1.3 is due Friday.